Hey everyone, welcome to This Explainer. Today, we're diving straight into something absolutely incredible, the completely invisible yet immensely powerful world of electricity. Just take a quick look around you right now. The lights, the screen you're watching this on, maybe a fridge humming in the background. It's so easy for us to take all of it for granted, right? But today, we're going to break down the complex physics behind this invisible force and translate it into simple, everyday concepts. But before we get distracted by all those cool devices that light up our lives, we really have to stop and ask ourselves one fundamental question. What exactly is electricity at its core? What is literally moving inside those transmission wires that connect a massive power plant to your living room? To figure that out, we've got a great roadmap today. We're going to start with the spark, or charge. Then we'll look at the flow, which is current, followed by the push, or voltage. After that, we'll cover the rules with Ohm's law, trace the path of circuits, and finally, look at how all of this scales up to power our entire world. All right, let's jump right into section 1, the spark, exploring electric charge. So our journey starts at the absolute smallest scale imaginable. We're talking about the most basic property of matter itself, electric charge. Picture a copper atom. Right there at the very center, you've got this tightly packed nucleus filled with positively charged protons. And orbiting around that nucleus are these rings of negatively charged electrons. Now here's the really cool part. In conductive metals, like copper, those outer electrons, they aren't held very tightly. They're actually quite mobile. They are essentially free charges, just waiting to be transferred and create an electrical spark. Okay, so how do they actually transfer? Well, think about when you rub two materials together, like, say, a glass rod and a piece of silk. When you do that, electrons actually jump from one object to the other, creating distinct positive and negative charges. And going all the way back to Benjamin Franklin's naming convention, there is a strict universal rule at play here, like charges repel each other, while unlike charges attract. It's basically the fundamental push and pull of the universe. Now, in physics, electric charge is governed by two absolutely non-negotiable rules. First off, charge is always conserved. That means it can never be magically created out of thin air, and it can't be destroyed either. It can only be transferred from one body to another. Simple as that. Second, charge is quantized. This means it always exists in discrete, indivisible little units based on the electron. You literally cannot have half of an electron's charge. It's an all-or-nothing deal. To really wrap your head around the sheer scale of this, let's look at this standard unit of electrical charge, the coulomb. Ready for this? Just one single coulomb of charge contains a mind-boggling 6 quintillion electrons. That is a 6 followed by 18 zeros, 6 times 10 to the 18th power. When you stop and realize just how incredibly tiny a single electron is, that number is honestly just staggering. Moving on to section 2, the flow, where we dive into electric current. When those billions and billions of static charges finally start moving together in a coordinated direction, that is what creates an electric current. The absolute easiest way to picture this is to use a water analogy. Think of it exactly like a current of water flowing down a river. But instead of water molecules drifting past a rock on the riverbank, electric current measures the rate of electric charges flowing over time through a metallic wire. In fact, if exactly 1 coulomb, those 6 quintillion electrons we just talked about, flows past a specific point in exactly 1 second, we call that flow 1 ampere. Next up is section 3, the push, also known as potential difference. Here's the catch, though. Electrons don't just spontaneously decide to move on their own through a wire. They're lazy. They need a physical force to compel them forward. We call this push potential difference, or as you probably know it, voltage. By definition, it's the work done to move a unit charge from one point to another. Going back to our trusty water analogy, voltage acts exactly like water pressure inside a pipe. It provides the necessary mechanical work, the electrical pressure, so to speak, to physically force those negative charges through a conductor. That brings us to section 4, the rules, covering Ohm's law and resistance. Now, a really crucial point here is understanding exactly how the push of the voltage and the flow of the current interact with the specific materials they travel through. And there's this beautiful principle called Ohm's law that ties it all together perfectly. Ohm's law states that the current flowing through a conductor is directly proportional to the potential difference, or voltage, across it. In plain English, if you increase the voltage push, the current is going to proportionally increase right along with it, as long as the temperature of the wire stays constant, of course. We can actually express this whole balancing act as a super simple equation. V equals I times R. Think of it like a seesaw. The push of the voltage, which we measure in volts, is exactly equal to the flow of the current, measured in amperes, multiplied by the pushback of the resistance, which is measured in ohms. And that pushback, or resistance, depends entirely on the material you're using. Conductors, like the copper wire inside your charging cables, offer very low resistance to the flow of electrons. They let the current zip right through. But on the flip side, insulators, like the rubber coating on the outside of that same wire, offer extremely high resistance. They essentially stop the current dead in its tracks. And that's exactly why we use them to protect ourselves from getting shocked. All right, on to section 5, the path, looking at electric circuits and their effects. So, how do we actually harness this controlled flow? We do it by giving the current a continuous, unbroken path to travel along. And this continuous loop is what we call an electric circuit. Take a look at this comparison here. On the left, you've got a real physical setup, a battery, some wires, a switch, and a light bulb. On the right is that exact same circuit, but drawn out as a theoretical schematic diagram. Engineers and electricians use these standardized symbols, like the long and short parallel lines for a battery, or those zigzags for resistance, to precisely map out these closed paths. And here's where the magic happens. Once that switch is flipped on and the circuit is completed, this flowing current produces some really remarkable, tangible effects in our world. For instance, it produces a heating effect, which is literally how your toaster or iron gets hot. It also produces a magnetic effect, creating an actual magnetic field right around the conductor. And, believe it or not, it can even produce a chemical effect, triggering chemical reactions when the current is passed through certain liquids. It's a true multi-tool of nature. Finally, we arrive at section 6, powering our world. We've spent a lot of time zoomed in on the atom, but looking at the big picture, where does all this voltage actually originate before it travels through hundreds of miles of transmission wires to reach your home? Well, let's look at India's installed electricity capacity as a great example of how modern nations solve this problem at scale. Giant power stations generate electricity by converting mechanical energy into electrical energy. And to meet the immense demand of millions of people, the grid relies on a very diverse mix of sources. As you can see, thermal power makes up roughly 67%. Renewable sources like solar and wind sit at 17.4%. Hydro comes in at 13.6%, and nuclear energy provides 2.1%. It takes a massive coordinated effort to keep the lights on. As we wrap up this explainer today, I really want to leave you with a thought to chew on. What fascinating, invisible atomic journeys are happening right now, this very second, inside the devices in the room around you. The next time you walk into a room and flip a simple switch on your wall, take just a moment to picture that invisible river of billions of electrons rushing in to power your world. It's pretty mind-blowing when you really think about it. Thank you so much for learning with me today, and as always, stay curious.